Hello students, welcome to Akshara 8 Foundation. So today we are going to discuss the new chapter, that is work, power and energy. Okay, work, power, energy. So today we are going to discuss about the work. Okay, so now our topic is work, power and energy. Power and energy. Work, power, energy. So first of all, we'll discuss about the work. Okay, what is the work? Okay, what is the work there? So work is nothing but when the force is applied on a body. So there is a certain displacement is taken place. Then we can say certain work done has taken place. We can say the work has done. Okay, so now it can be defined as. So when the force is applied on a body, there is a displacement in the body in the direction of the applied force, then we can say there is a work has done there. Okay, the work is said to be done when the displacement of a body takes place in the direction of the applied force. Okay, is called the work there. Okay, so then, so we can write here simply it can be defined as the work. Work is equals to work done. Work done is equals to force into displacement. We can write here force into displacement. Force into displacement. Force into displacement. Okay, so this force into displacement we can write. This is the force into displacement. Work done will be denoted by the W, that is equals to force is denoted by here F and displacement is denoted by S, and it is also defined as the dot product of the force and displacement vector. Okay, so it can also defined as the work done. Work done is equals to dot product of force vector and displacement vector. Okay, work done is also dot product of force vector and displacement vector there. If it is a dot product, then how can we write there? W is equals to F bar dot S bar. This is equals to Fs into cos theta. We can write there Fs into cos theta. So this is a work done definition of the work done there. What is the SI unit of work done? So SI unit of work done. SI unit of work done. So it can be written as. So always we'll get the SI unit from the formula there. So force SI unit is Newton and displacement SI unit is meter there. So we can write here Newton meter. Okay. So Newton meter. So it can also be written as here joule. So Newton meter is also said to be the joule there. Now the dimensional formula. So dimensional formula of. So dF is nothing but here dimensional formula. Dimensional formula of work. Dimensional formula of work is. So from the SI unit, we are getting this dimensional formula. Dimensional formula is nothing but the expression of a physical quantity in terms of the fundamental physical quantities and with their powers. Okay, so that is called. See here Newton. Newton is nothing but what can we write here? Kg meter per second square. Kg meter per second square. Kg meter per second square. Meter and meter. Meter square will be there. So kg meter square per second square. So we can write here m power 1, L power 2, T power minus 2. This will be the dimensional formula of the work done. And this work done is a scalar quantity. So this work done is a scalar quantity. Why it is a scalar quantity? Because it is the dot product of the force vector, two vectors. Scalar quantity. Okay. So work is a scalar quantity. It is the dot product of the force and the displacement vector. So it is a scalar quantity. And this work can be positive, negative and even zero also. So work can be positive, it can be positive, comma negative and even zero also. So 0 work done, positive work done, negative work done will be there. Okay, now we'll see there. So when it will be the positive work done, we'll see here by the example like this. So positive work done, positive work done. So positive work done, we can write like this. Suppose a body is there here. If a body is there of mass m on the floor, on the ground there. Here, if the force is applied on the body, certain force F is the force is applied here, and here in this body there is a displacement will be, the displacement of the body will be taking place. From here to here there is a displacement of the body is taking place. Here the force is applied, then in the direction of the applied force the body is moving, then we'll get the positive work done, because here the angle between this force vector and the displacement vector is here 0. So theta is equal to 0 degrees here in this case. Then work done formula what we got there, Fs cos theta, no? Fs cos theta. So then here we can add there Fs into cos of 0 degrees, cos 0 degrees. So cos 0 degrees how much there? Since W is equals to Fs, this is the maximum work done. W maximum work done will get there here. Since this cos 0 degrees is equals to 1. Cos 0 degrees is equals to 1 there, okay. So now negative work done, okay, negative work done. So here we can see any object, any force on the object is the force applied there, pushing and pulling, okay. If you push the body in the direction of the body there, so the displacement of the body in the direction of the force only, it will be moved there, the displacement will be there in the direction of the force, then we can say there is an example for the positive work done there, okay, even in the pushing or the pulling there. Suppose it is pulled like this, so in the same direction of the applied force, there is a displacement of the body will be takes place, then we can say it is a positive work done. So now negative work done, we will see here negative work done, negative work done, negative work done. So now negative work done means, suppose the force is applied, okay, force is applied downward direction and the displacement of the body may be upward direction there. So this is applied force downwards and displacement will be upward there. So now here the angle between these two is theta is equals to 180 degrees here, theta is equals to 180 degrees. What is the example here we can take there? So while we taking the water from the well there by using the bucket and the rope through the wheel and axle of the wheel of the well there, so there we apply the force downward direction, the bucket will be moved upward direction there, okay. Even now the crane is taking the objects from the, okay, from the sea or from the lakes, okay, if anything is fallen in the lakes or in the sea, from there the force will be applied downward direction and the objects will be displaced upwards, okay. So then the angle between the force vector and the displacement vector is 180 degrees. So then that force is called the negative vector. See here how we'll get there. W is equals to F into S cos of 180 degrees. So we know that cos of 180 degrees how much there? Cos 180 is minus 1. Cos 180 value is minus 1. So therefore here we'll get there. This is the negative work done. W is equals to Fs into minus 1 will get here. So therefore that is minus Fs. So this is the negative work done there. This will be the negative work done. And we can say this is a maximum work done or positive work done, we can say. It is a positive work done or maximum work done. Okay. This is the minimum work done, we can say here. This will be the minimum work done. What is the minimum work done? Minimum. Okay, now we'll see there is zero work done. In the which cases the work done can be 0 here. Okay. Suppose if I hold a suitcase in my hand and if I move, or if I hold in my hand and I am standing here, okay. So in that case, so I am holding means the force is acting here. If I hold here, the weight of the suitcase will be acted downward direction. That is the force due to the gravitational, okay, force due to the earth. It will be act downward direction. Then there is no displacement. Okay. Suppose if I move by holding a suitcase in my hand, if I move right side or left side, so without changing the height of that, then the displacement will be in perpendicular to the force applied force direction. Okay, then in that case it will be 0 there. Suppose here an object is there here, the weight is acting downward direction, that is mg, and this the displacement is in this direction there. So here the angle between these two vectors, angle between here it is a 90 degrees, no, angle between the force and the displacement vector it is theta 90 degrees, then the work done will be 0. Okay. So now here in this case this is a 0 work done, 0 work done, and the 0 work done. So theta angle between the force and the displacement vector is 90 degrees. Then we know that W is equals to Fs cos theta, we can add then Fs cos theta. So then W is equals to F into S cos of 90 degrees, cos 90 degrees. Then cos 90 value will be 0 here. Okay. So here we can add the Fs now. So Fs into, we will write here 0 since cos 90 value will be 0. So therefore we will get the W. So that is a 0 work done. So it is a 0 joules. So like this, these are the different work dones, a positive and negative, and there 0 work done will be takes place there. Okay. So now suppose we will see here next. Suppose if the force is acting, the pulling force, the force is acting on the body. So with certain acceleration, with certain angle here, with certain angle with the horizontal. So this body has a mass m, and by application of this force, the body will be moved on the floor up to certain displacement. So here in this case, what is the work done? So we'll get the same formula there. Okay, so the body, it is applying the the force is applied on the body at certain angle with the horizontal, but the motion of the body is along the horizontal only, no. So here we have to take the Fx we have to take that. Fx is nothing but Fx. So work done is nothing but, we can add here Fx into S, we can add here. So Fx is nothing but, we will get, so from the right angle triangle, Fx is equals to, so cos theta if you apply then, cos theta is equals to, so this adjacent component. If I write here the work done, no, right angle triangle will get here. This will be the right angle triangle, from that Fx divided by, so cos theta is nothing but adjacent by hypotenuse. Fx divided by F will get there. From this, Fx is equals to F into cos theta will get there. F into cos theta. So therefore, from this we can write here F cos theta into S will get there. So therefore, from this W is equals to Fs cos of theta. So this is a work done. This is the first case. Okay. So different cases, here we are discussing the different cases, and different cases work done. So let us consider this is the case 1, first case. Okay. So now we are going to see the next case, work done. So second one is work done to lift the, work done to lift an object of mass m. Okay. So consider here an object is there like this. If an object is there here and it has a mass m there, okay, then if it is lifted to a certain height there, if it is lifted to a certain height here h, so this block is lifted here like this. Okay. So then here the weight will be act downward direction, here also weight will be act downward direction always. Here weight is nothing but here mg, no, mg. So that is the force is acting here, and weight is acting downward direction, and force to lift the object here. Here we can consider there, while it is lifting there are two work done will be there. So first one, in this first one, work done by the gravity. Work done by gravity. Work done by gravity. So work done by gravity, it can be given as Wg. We can write here Wg is equals to, so force is acting downward direction and displacement is upward direction there. Displacement is upward direction. So there, so here mg h cos of 180 degrees, we can add here cos of 180 degrees. So Wg can be written as here minus mg h. Okay, but while it is lifting, it cannot be lifted by itself. So gravitational force always it is pulls down. So against to the gravitational force, certain force we need to apply to lift it. So then work done by the person then, okay, work done by external force, we can say external force. So here we can add there Wg Wf, that is equals to, we can add here mgh. So there applied force is upwards, here, then displacement is also in the same direction. So we'll get there applied force is which is equal to the acceleration due to gravity. No, that should be acceleration due to gravity. Then displacement is here h and cos. So work done by the gravity on the inclined plane. So here if the inclination of this inclined plane is theta, then weight of the body can be resolved into two components, that is mg cos theta and mg sin theta. Then mg sin theta will be back downward direction, and if the block has lifted upward direction, then the work done by the gravity is mgl sin theta there. Suppose if it is sliding downwards, due to the weight, if it is sliding downwards, then here we can say there is a positive there, work done by the gravity while it is sliding down. So mgl sin theta will get there. It is in the case of sliding down. So this is a sliding up, and this one will be the sliding down. Okay. So this is about the work done by the gravity there. Okay. If the inclination is theta of the inclined plane, so the weight of the body can be, always weight will back downward direction. Here this will become like this, 90 degrees, and this is a 90 minus theta. If this is a 90 minus theta, means this also 90 minus theta, this will become theta. Okay, so here this is the adjacent component. Perpendicularly, this vector has to be resolved into two components, horizontal component and vertical component. Horizontal component of the weight is mg cos theta, and the vertical component of the weight, it can be written as here mg sin theta there. Okay, and if this body is moving upward, sliding upward on the inclined plane of length L, so then the work done by the weight, work done by the gravity to slide up of the inclined plane of length L. So then minus mgl sin theta, while it is sliding down, it is mgl sin theta will be there. That is the next case, work done by the gravity on the inclined plane of an object there. Okay. So now next one we'll see there. So what is that? How many cases we completed? Third one, no? Fourth one. Now, fourth is work done by the horizontal force of a simple pendulum. Okay. So we know that simple pendulum is nothing but it is the metallic spherical body which is suspended from the rigid support like this. So now this body has certain mass and it is in the shape of a spherical, and this has a length L here, from here to the center of the bob, center of the spherical body. Then if the horizontal force is applied here, then it will be move like this, it will move, keep on and applied and released, horizontal force is applied and here it is released there, then it will be keep on moving oscillations there. While it is moving there, this spherical body will be lifted to certain height. So this is the height it can be lifted. That height, if you write here h, so then while horizontal, due to the horizontal force, it can be lifted. Okay. So then what will be the work done? Okay. So here the weight will back downward direction, always downwards, and here also the weight will back downward direction. Then this has the length L, and it is making an angle theta while the horizontal force is applied. So this pendulum, the rope or the thread or the string of this pendulum, it will be taking vertical. There is an angle theta with the vertical there. So now here what can we write? This can be written as here. So this is a horizontal force, it can be written, and there is a tension will be there in this string. Okay. So this is the, we can write here, this is theta. If this is theta, this also will be theta, no, alternate angles there. So then this will become horizontal component, t cos theta we can write, and here this will become, here we can write there t sin theta, t sin theta. It is a vertical component and this is a horizontal force. So what can we write from these two equations? So F is equals to t sin theta is a one equation we can write there horizontally, and the vertical component, that is mg. mg is equals to, we can write here t cos theta we can write there. Now if I divide these two equations, what will get here? Sin theta, t sin theta, t sin theta is equals to f divided by t cos theta is equals to mg. Okay. So now T will be cancelled here. We will get here tan theta is equals to f by mg. This we have seen there in the case of Lamis theorem. We have seen there, no, tangent law. By using the tangent law, we will get here. Here work done. We are going to see here work done by the this horizontal force. Work done by the horizontal force. Okay. So work done by the horizontal force. So simply we can write here, no, force can be written as here W is equals to mg into tan theta we can add there, mg into tan theta. Okay. So work done we have got there now. So then here h, how much displacement of this body has taken place? H distance, h, it is moving upwards. Okay. Then mg this horizontal force is applying here, horizontal direction, that is in terms of the mg, weight is acting downward direction, and it is moving upward direction. So here we can add there, suppose this is a L distance, no, this has moved here x, no, this we can write here, what can we write there, this we can write here L minus h we can write now, this is a h means, so this distance here L minus h we can write, L minus h. Okay. This is the distance of L minus h we can write, and here this will be the suppose if it is move here x displacement. Okay. So h is equals to this, h is equals to what can we write here, total length is L, and h can be written as here, okay, we consider like this, will be consider there this equation. So we will write this one as, I'll write like this, this is the length L, and consider this is a y. Okay. So what can we write here? Y is nothing but total length minus this h we can add there, total length minus h, no, and this is a L here. So from this y is equals to L minus h we can add here. So this is equals to, or otherwise we can add L minus h only, no problem. So L minus h we can add L minus h, and this will be the, this is a x distance, it has moved there. Then tan theta is equal to what can we write there, tan theta. So in this tan theta from the triangle, tan theta is equals to here x divided by L minus h we can add there, L minus h. So now the horizontal force here, it can be written as here, what can we write, horizontal force mg into tan theta is nothing but x by L minus h we can add there, x by L minus h. Okay. So now the work done. So work done is equals to W. W is equals to, we can write here, so W is equals to force into here we can add there h. So then work done we can add here, force is what we got there, mg into x by L minus h we can write here into h. So otherwise we can write here, this one we can write here mgx h by L minus h we can write there. So this is the work done by the horizontal force, or we can write like this also, this equation. So here the horizontal component here, if you want find out, it has lifted h, no, h distance it has lifted there. Okay. So it can be written as cos theta. We can write here cos theta is equals to in the diagram there. So cos theta is, we want this, no, this one, okay, here horizontal component of velocity, we can write here L minus H divided by hypotenuse, okay, we can write here hypotenuse is what, the L, so L minus H is equals to, we can write here, that is a L into cos theta, we can write L into cos theta, L into cos theta, we can write cos theta, no? So now here H is equals to horizontal force, what we got there, horizontal force, F is equals to mg tan theta, we got mg tan theta, W is equals to, we can write here W is equals to F. So the weight is what here, mg, so mg is acting here, mg into, so this H, no, displacement is here H, displacement is H here. So from this equation, what can we write here, L minus L cos theta, L minus L cos theta is equals to H, we can write now, L minus H cos theta is equals to L minus L cos theta is equals to H, we can write there. So from this, so here H is equals to, what can we write there, W is equals to mg, W is equals to here mg, and H is nothing but L, if you take common there, 1 minus cos theta will get there, 1 minus cos theta. So here the work done by the gravity, is the, this is the expression there, work done by the gravity is W is equals to mg L cos theta, okay, and here the force is acting downward, displacement is upward, no, so minus will get here, minus will get here, minus mg, this value will get there minus, force and displacement will be in opposite direction, and work done by the horizontal force, here we can write like this, okay, mgx H by L minus H cos theta. Okay, this is about the work done by the horizontal force of a simple pendulum. Work done by the horizontal force and the work done by the gravitational force. Okay, two cases we have seen there. Next case we are going to see here. Next different cases we can see. So next case is the fourth one, fifth one. So we see here the fifth case. Work done to pull the L length and m mass of the chain placed on a horizontal frictionless table, work done to pull the L length of the mass, L length and mass of the chain placed on a horizontal frictionless table. Okay, so work done. So this one, and here L length of the mass, to pull the L by nth, here we write like this, L by nth part of length, part of length, and okay, L by nth part of length and mass of the chain, m mass of length placed on a horizontal frictionless table there. Okay, so then we'll see that. So it is placed like this. So this is the horizontal frictionless table, and here L, total length of the mass, total length of the chain, if you consider there, L length of the mass. Okay, L length of the small l is the length of the chain, and small m will be the mass of the chain there. Okay, so total L, total length is here L. Then so this part of the length. So now consider this part of the length. It is suppose x there, x part of the length there, and this one it will become L minus x part of the length. This will be L minus okay length. So here weight of this part of the chain. So weight of the part of the chain will be how much there? Here it will be. So at the center of mass means here the length will become how much there? So this length will be here x by 2, x by 2 length, x by 2 length it will be there. Okay, now the mass of this part, mass of the part. How can we write the mass of the part? Linear mass density. So we can write here lambda, mass per unit length. So mass of this part of the chain is m dash we consider there, that is m dash divided by the length of that path is here L. Okay, so now here m dash can be written as here, how can we write m dash? M dash is equals to m by L into x, we can write that, m by L into x, m by L into x we can write that. Okay. And this is the 1 by nth part. So here 1 by nth part we have said no, L by nth part. So here this is a L by nth part, means x by nth part we can write here there. So L by nth part means here if you write here L by nth part, L by nth part, then this part will become how much there? X by 2 is nothing but this total length will become, this will become L by 2n, no? L by 2n displacement. The displacement means the center of mass will be at the exact at the half of that length there. So L by 2n will be, it will be there. Okay. So now here the weight of this part will be what there? M dash into g, no? M dash into g there. So now here W, here weight is nothing but W is equals to m by L into x into g, we can add there. Okay. So now this is the weight. Weight is nothing but it is a force acting there. Force acting by the gravity. Okay. There is a force acting by the gravity. And how much distance it can be moved there to pull L by nth part. L by nth part here. Okay. L by nth part means L by n. Okay. So means x. So now here we can add there. How much displacement will be takes place here? This L by 2nth of the displacement it can be takes place, no? Okay, so here we can add there now x is equal to L by nth part we have written there. So now here this one we can write here m by L into x is nothing but L by n into g will be there. So this and this will be cancelled there. Then here this is a force. Weight is nothing but it is a force acting by the gravity. Will get there mg by n will get there, mg by n. And what is the displacement here it is taking place? Displacement will be L by 2n displacement there. So now the work done by the gravity can be written as here, that is, so force mg by n into here the displacement will be L by 2n. So therefore the work done, and the weight it is acting always downward direction and it is moving, the displacement will be upward direction. So we can write here minus work done by the gravity is minus mgl by 2n square will get there, minus mgl by 2n square. Okay. So this is the work done to lift the n by 1 by means L by nth part of the chain, to lift it onto the table over the edge of the table there. Okay. So that is the work done to pull the L by nth part of the length of the chain, and mass of the chain is here small m, placed on the horizontal frictionless table. Okay. So here this is a work done to pull the object, to pull the chain. Okay, now here we will discuss there few more formulas. And suppose here this is a L by nth part there, L by nth part which is hung over the edge of the table there. So from this which is hung over the edge of the table, L by n1th part of the chain to lift there, not whole length of the part there. Part of the chain has to be pulled upwards. Here it is this, you consider this is the first case, and here second case we can add there. So within the part of the chain which is hang here over the edge, so from that certain amount of the length has to be pulled. Okay, means let us consider here L by n1th part of the chain to pull it onto the table, then work done. So then the initial length of the part, it can be written as here L1, N1, L by N1 we can write here. Okay, and the remaining part to pull it up. So in this way, similarly we will get here. So work done by the gravity, that can be minus. So mg L minus mg L by 2 will get here. So that is 1 by N1 square minus 1 by N2 square will get there. This is the second case in this only. Means it is the work done to pull the not complete hung part of the chain. It is the certain length of the part to pull it up, okay, onto the table there. That is the formula is minus mg L by 2 into 1 by N1 square minus 1 by N2 square. Okay, that is the work done to lift the nth 1 by nth part of the chain of the 1 by nth part of the chain. Okay, so remaining concept we'll see tomorrow, and we'll do the numericals. Thank you children, have a nice day.